So today we are going to start doing integrals with these. We just covered the derivatives. And we're going to be finding the areas that are inside all those little loop-the-loops, which is actually kind of cool. So if your graph is continuous, and instead of A and B, we use alpha and beta, just since they're angles. And it's saying the difference between them has to be smaller than 2 pi. If you go more than once around, like you start accumulating the same areas again. Does that make sense? Like you overlap. So anyway, the difference between them has to be smaller than 2 pi. And I just want to show you how this works real quick. I just got another piece of paper. You don't have to write this part down, but just watch. In rectangular, coordinate plane that looks like that, you would have your function do blah, blah, blah. And say we wanted the area from A to B. It would be all of this, right? And you kind of view it like sweeping left to right. We're accumulating all this area, okay? For polar, it doesn't work like that. If you have, this loop-the-loop thing, I don't know, that was a really awful, let me try again. Let me try and do like a 4-leaf clover thing. There we go. A little bit more careful on that one. When you go to find the areas of these, like say you want the area of the first petal, it's not a sweep left to right. You're rotating. So you start here and you rotate to get the area. Does this make sense? Okay, so it's a rotation, not like a sweep left to right, because it's polar, not rectangular. Gosh, I really messed up that one graph. I just kind of drew a big squiggle. But anyway, here is your formula. It is 1/2 integral alpha to beta. Alpha just looks sort of like a little fish. Beta is like a fancy curly V there. R squared d theta. This is 100% guaranteed to be like kind of a heavier topic on the AP exam. It will show up and it's usually on the free response part. Okay. Like this formula is going to be on there. You're going to have to find some areas. When finding your intersection points, like you have 2 different graphs, always sketch a graph. Like draw a picture. And I'm going to show you why in a second. Sometimes they can intersect at a place that you weren't expecting because it's at a different amount of rotation for each of the 2 graphs. Also, you always want to check the pole because that's 0, any amount of rotation. So just things to be aware of. So we're not even going to find any areas yet. We're just going to practice doing intersection points. Now, typically in like rectangular land, if you want to find the intersection of 2 graphs and you don't have a calculator, what would you do with them? Set them equal. Okay, so we're going to start by doing that here. Do you see how we have R equals all of this and then R equals 1? Okay, we're just going to set those equal. So you would have 1 minus 2 cosine theta equals 1. And we're going to just work that out. So what would you do to start solving this? This is like, welcome back to pre-calc. Yep, minus 1, which is going to give you 0, which is actually kind of nice. Divide by -2, but 0 divided by anything, just 0. And so where on your unit circle is cosine going to be 0? There's 2 places. We want to think the whole way around. Yeah, pi over 2 is one of them, and 3 pi over 2. Okay. So if we're thinking of like an actual coordinate point in polar, you can plug these back into either one, but this one's obviously a whole lot easier. R equals 1. I mean, it's just going to be 1. So you get 2 intersection points, 1 comma pi over 2 and 1 comma 3 pi over 2. And if you're like, oh, those are the only intersection points without drawing a graph, then you're going to miss one. So I just want to show you what this looks like when we go to draw a picture. And I think sketching graphs is something we could always use more practice with. So go ahead and make a little table, theta and R. And I'm just going to plug in the quadrant angles for this one. So if you plug in 0 pi, and I'm just plugging in for this first equation here. If you plug in 0, cosine of 0, 1 times 2 would be 2. And so 1 minus 2 would be -1. Again, I'm just going to do the quadrant angles. Cosine pi over 2 would be 0. So 1 minus 0 would just be 1. How about pi? Cosine of pi. -1. So the negatives are going to cancel. You'd have 1 plus 2. So 3. And then 3 pi over 2, again, that would be 0. 1 minus 0 is 1. 2 pi is going to put you back where you started. If you want to put that on your table, you can. If not, it's going to just put you back where you started. So let's just draw a little picture. This will also be good practice plotting points. So if you rotate nowhere, 0 pi would be this direction, but it's -1, so we went the opposite way. So it's going to be right here. Pi over 2 would be up, and if we go 1 in that direction, that's going to be right there. Pi 3, so pi would be this away, and we go 3 in that direction. So to give you an idea of what this is going to look like so far, because it's going to loop around, we can't get from this point to this point without going through the pole. So you're going to have to go through the pole to get there, and then it looks kind of like a snail. Because I can't connect those 2 points and then get back around to this one without going through the pole. And then 3 pi over 2 would be in the downwards direction. We go 1 in that direction. And then we end up back where we started, which again, you can't get there without going through the pole. Looks like a cute little heart. Oh, and I was going to color code. That's why I got these markers out here. Let me make that one green for what it's worth. Now, what would r equals 1 look like? Like if you're 1 unit away from the pole all the time. So, oh, and specifically, what kind of circle is it? Because it's 1. It's the unit circle. Isn't that cool? It's the unit circle. All right, so you're going to be 1 unit away all the time. So it's going to look like this. So the point I'm trying to get across here, this is the big takeaway. We found these 2 intersection points. Do you see how they intersect there and there? But there's a third one. Okay. So this intersection point, let's see, that would be 1 comma pi. I always want to say pi comma 1. It would be 1 comma pi on r equals 1. But it would be the starting point. It would be this one, -1 comma 0 pi on r equals that other thing. Sorry, I ran out of space there. So do you see how one of them's at 0 pi and one of them's at 1 pi? They do still intersect there, and that's why it's always important to draw a picture. That's the big takeaway. Are we together on that? Draw a picture. If you don't get a calculator for the problem, you have to do it by hand. Now, these are some useful formulas. I don't really expect you to memorize them, but I'm just throwing it out there because sometimes you can't do your antiderivative without them. So there they are. All right. So we're going to now find some areas. Find the area of 1 petal, that's like 1 little leaf, of this graph. Now, it's one that we did already, but again, I think we could use the practice with, sketching a graph. So let's make ourselves a table. We'll start at 0 pi. And I know it's going to be they're called the roses because it says 1 petal of it. All right, so if you plug in 0, what do you get? Two. Good. Cosine of 0 is 1 times 2 is 2. Now you could just go and do the quadrant angles, but you're going to kind of miss out on some of it. Do you see how there's a 3 there? I would do the 6. Like, let's go to pi over 6 and pi over 3. Okay. Like, that's how I usually make that decision is, well, what does the equation look like? All right. So if you plug in pi over 6, when you multiply it by 3, you immediately get 3 pi over 6, which is pi over 2. Cosine of pi over 2 is 0. Cool. If you plug in pi over 3, immediately the 3's cancel. You just get cosine of pi, which is -1, good, times 2, -2. And then if you plug in pi over 2, not all the way to pi yet, it would immediately be 3 pi over 2. And cosine of 3 pi over 2 would be 0. I think that'll be good enough for us to like get the hang of what's going on. Let's just go ahead and graph that. Because once you get them started, usually you can kind of like keep it going because it's going to keep looping around. So 0 pi and then 2 in that direction. So that's going to start us here. And then we're to the pole because it's 0. So it's gonna start here and kind of go like that. And then you'll kind of have to watch me point to it for this one. Pi over 3 would be like this way. You don't have to dot that in. I'm going to end up erasing that. Pi over 3. Do you know on your quiz you just took how it had like the dotted lines in it? Okay. Anyway, pi over 3 would be like right there, but it's -2. So you're going to go 2 like in this direction. So it's going to put you down here-ish. I mean, you know, I don't have a polar grid on this paper, so it's like good enough. So we're going to go down to there and then back to 0. And then hopefully at that point, we can kind of just keep it going. Like we're going to get one more petal over here and then end up back where we started. So like once you get it started, usually you can kind of keep it going, but you need the visual. If you don't have the visual, you're not going to be able to see what you're doing. Now we're going to find one petal of that. If they asked you for all 3, you would still just find one and then like multiply it by 3. There are a lot of different ways you can do this, but I think the easiest is to just do one petal. Now remember we started here. So if you start doing this rotation, you're only going to get this piece. Does this make sense? Okay. So I want to start when I got to 0. Look at your table. At what angle of rotation did we get to 0? It's pi over 6. And then we kept going around and we want to get all this area. So we keep going around. When did we get back to 0? Pi over 2. Okay, so when we set up our integral, those are going to be our boundaries. And it's really hard to see that if you don't have a graph, okay? So look back at your formula. It's 1/2 integral r squared d theta. So we have 1/2 integral pi over 6 to pi over 2. And then r squared. So it is, and again, like, you know, I'm all about setting things up blank. Like sometimes it's a good idea to do that. And then just put this into those parentheses. And then we have the fun job of working that out. So first you have to square what's inside of here. So 2 squared would be 4 times 1/2 would be just be 2. So 2 and then integral pi over 6 to pi over 2. And then this would be cosine squared of 3 theta. Do you know how I've harped on you guys about u substitution? And we've done like a zillion u substitution problems. It's not going to work here because you know how when you do a u substitution, whatever the derivative of u is has to be in the problem. Like you have to be able to find that somewhere. That's not going to happen here. That's why I gave you these useful formulas up here. Do you see how this is cosine squared? Here we have a cosine squared. Okay, I'm going to use this formula to substitute this out so that I can get something I can actually do an antiderivative of. Okay, so cosine squared is 1 plus. Now it says cosine 2 theta. So you have to double this, but it's already 3 theta. So for us, it's going to be 6 theta. Good. You just double that. And then over 2 and then d theta. Gosh, I can't write today. So what do you notice is going to cancel? The 2's are going to cancel out. And now we can do the antiderivative. Okay. Do you remember when we did an antiderivative of just 1 and it would be x? Now it's, oh, good. Perfect. Usually that's like pulling teeth, but it seems like you're with me. Okay. So this will be theta plus, I'm going to wait and see what you've got for me. How would you do that antiderivative? It will be sine. I need something in front of the sine though. 1/6. Yep. Good. To adjust sine 6 theta such that pi over 6 to pi over 2. That's what I thought you said, 1/6. Oh, did you say 6? Okay, well, you knew something was going to have to go there. All right, and now we're going to do upper boundary minus lower boundary. So if we plug in pi over 2, well, that'll just be pi over 2 plus, let's see, if you plug in pi over 2 and multiply it by 6, that'll be what, 3 pi? If you think about going around your unit circle, this would be 1 pi, 2 pi, 3 pi is going to put you in the exact same place as 1 pi. And sine of that would be 0. And then lower boundary, this would be pi over 6 plus, I think the same thing is going to happen here. Yeah, the sixes would cancel, sine of pi is 0. Let's pretend it was multiple choice and you couldn't leave the answer like that. And you're like, why is she torturing us? Well, if it's a multiple choice question, you're going to have to actually like do the fraction. Pi over 2 minus pi over 6. A half would be how many 6? 3 6 minus 1 6, 2 6, which is pi over 3. So the area of this little puddle is pi over 3. Cool, let's try it again. This time you got a picture. That's like a gift. You don't have to draw one. Let R be the region in the first quadrant bounded by this equation. Oh, you should also be really happy that there's a square root. Why is that a good thing? We're going to square it and then they'll just cancel out. Okay. What is the area of R? Well, we need our boundaries and we start at the pole. Watch me point to this. We start at the pole, we go around and we end up at the pole. Okay. So we're going to take this equation and set it equal to 0. Because we're trying to get our boundaries. I don't know what boundaries to put on the integral until I know what those amounts of rotation are. So, you know, you would square to get rid of a square root. That's still going to be 0. You would divide by 6. That's still 0. That's like the nice thing about 0 is all that stuff kind of just goes away. And so we're going to have 3 theta equals what? Where would sine be 0? Zero pi and pi, and 2 pi and 3 pi and 4 pi and forever after, but we only need the first 2. And then to get theta by itself, you would divide by 3. So 0 divided by anything is still 0, and then pi over 3. So those are going to be the boundaries on our integral. So what's the formula to set it up? What goes out front? 1/2 integral, and then those are our boundaries. And then it'll be R squared d theta. And then you can just copy this into there. But again, the squared and the square root are going to cancel. So I'm actually going to clean that up a little bit. Those would cancel. You would have 6 and then out front a half. So half of 6 would be 3. If you're good doing that in your head, that's cool. I just kind of wanted to clean it up a little bit so it looked a little nicer. Now we're going to do the antiderivative. So antiderivative of sine. You need a function that if you did the derivative, you would get sine. It would be negative and a cosine. What adjustment would you need for this 3? You would need a 1/3. But there's a 3 out front. So the 3, you would need a 1/3. Like what was the other one? Did we had a 6 and we needed a 1/6. So this one's a 3. You would need a 1/3, but the 3 that's out here and the 1/3 are gonna, like, they'll cancel out. All right, so it's just gonna be negative cosine 3 theta such that, and then we're gonna evaluate. So upper boundary minus lower boundary. All right, so if you plug in pi over 3, the 3's are going to cancel. Cosine of pi, -1. Oh, but it would be 1. And then if you plug in 0, cosine of 0 is 1, but it would be -1. Now you can't get a negative area. What is that going to all boil down to? The area is 2. The area of this is 2. That's so cool. That's neat. That's neat. All right, I'm going to say 4 for last because I think that's the toughest one on here. We're going to go down to 5. This is a multiple choice question. Look at this graph. Isn't that neat? Cool. It looks crazy. All right. Anytime you're doing polar stuff and they give you a graph, you need to be like, yes, I don't have to draw a graph. Like they gave me a graph. So they give you these 2 graphs. Which one of these integrals gives the area of the region between them? So we're actually looking for this area and we're not even finding it. It's just the setup. Okay. But isn't that cool? We're finding that area. Neat. Okay. So 1/2 integral Now, usually you'd have to think about the boundaries, but look at your choices. They're all 0 to pi, so it will be 0 to pi. But do you see how these both involve sine? That's because that equals 0 at 0 and pi. Okay, so 0 to pi. And then it's going to be something squared minus something squared d theta. That should feel familiar. We've done something really similar to that. Do you remember when we did the volumes of the rotations and we spun them around? Washer method, discs and washers, remember the donuts? Anyway, we're going to do the bigger one minus the smaller one. So look at the problem. Which one's do you think, the bigger one? Yeah, 4 sine squared. And then the other one is 2 sine squared. And we just need to like simplify that until we get one of these answer choices. It won't be too bad. In fact, we can like talk our way through most of it. When you square this, 4 squared, 16, and squared would be sine to the 4th. So 16 sine to the 4th, and then this would be minus 4, because 2 squared is 4. So 16 minus 4 is 12. And then you would just multiply by the half that's out front. So which answer choice did we end up with there? D. It's the only one that had a 6 in it. So cool, we didn't even have to work it out. It just was the setup. And I think actually we're going to kind of just mostly do the setup for this one too. I think I'll go until we get the antiderivative, but this problem does get really messy. But we can't just avoid the messy problems. You know, they're going to give you messy ones on the AP exam. Okay. So first thing we need to do is draw this. Anytime they give you a graph, you need to be like, yes, they gave me a graph, because otherwise you have to draw one. You really can't do this without a visual. And if you don't get a calculator, like if it's on the non-calculator part, you have to do it by hand. All right, so let's start with 0. Sine of 0 would be 0. So the result of the whole thing is 1. And I'm actually going to kind of like keep a picture going at the same time, because sometimes if you just get these started, you don't have to plug in too many numbers. Like you can kind of get the gist of it. So 0 pi and then 1 in that direction. Now I'm just going to do the quadrant angles. I'll just go to pi over 2 because I don't see anything in here with the theta. Like if there's a 3 theta, I would be like, oh, let me try all the 6th. Or if there's a 2 theta, I would be like, oh, let me do pi over 4, you know, but there's nothing in there. All right, sine of pi over 2, 1. So that'd be 1 minus 2, negative 1. Okay, so pi over 2 would mean you'd want to go in this direction. But because it's negative, we're going to go in the opposite direction, and that's going to put us down here. You can't connect from there to there without going through what? The pole. You have to go through the pole. So we are going to go through the pole. It's going to do something like that. They're really loopy. All right, then let's do pi. Sine of pi would be 0. So the result of the whole thing is 1. If you go 1 in the pi direction, that's going to put you here. Again, you can't get from there to there without going through the pole. And do you guys kind of get the gist of what's going on? It looks like one of those hearts. Like this is going to come down here and then come back. I don't know how far, but it doesn't really matter. We just needed a visual. Are you coming with me on that? I'm trying to save you some work. Like if you just do enough points, I'm sort of telling you to be lazy. Just do enough that you can figure out what it looks like. Okay. It's going to look something like that. All right, now what was the question asking? What are we doing? Find the area, between the inner and outer loops. So it's kind of similar to this one. We want this area. So it's the whole thing minus the part that's inside. So it's going to be, you know, kind of similar to what we just did. We are going to have to set up 2 different integrals though, because the amounts of rotation are going to be different. Okay. So let's do actually a setup. We're going to have 1/2 an integral of r squared d theta for like the outside part. And then we're going to have minus another one for the inside part. So just like set it up blank. You're going to have 1/2 integral r squared d theta minus 1/2 integral r squared d theta. You can't put them in the same one this time. Let me do a compare and contrast here. Do you see how this one, we started at 0 and came around to pi, and we started at 0 and came around to pi for both of them? Like the boundaries were the same. This one's not going to be the same. Like they're different. You have to set up 2 different things. What's the R that's going to go in both of them? Well, it's that, right? So those are going to be the same. And then we just need to figure out the boundaries. We'll just do the setup for this one because this problem gets really messy. We'll just do the setup. As long as we can get it set up, we're good. Are we good so far? How we got that? Set it up blank and then kind of just fill it in. Let's do the little loop first. That's going to be the one that we're subtracting out. We started here. That was at 0 pi. And then we went through the pole. Oh, I didn't figure out where that was. How could we figure out where that is? How could I figure out where this goes through the pole? Yeah, set R equal to 0. So it'll be 1 minus 2 sine theta equals 0. I didn't happen to find that number on my table, so I got to go back and find it. All right, welcome back to pre-calc. What would you do to start solving it? Yep, -1. Good, so the negatives will cancel. And so we need to find places on our unit circle. There will be 2 of them where sine is a half. Good, pi over 6. And then the other one's in the second quadrant. Pi over 6, good. So look, watch me point to it. We started here, that was 0 pi. We got to the origin at pi over 6. We looped around, we got back to the origin at 5 pi over 6. Do you see what I'm saying there? Okay, so for the little loop, those are going to be our boundaries. For the bigger loop, and watch me point to this one. I can't start at 0. If I start there and rotate, I'm only going to get this little piece. That's not good. I want the whole thing, okay? So if this is pi over 6, I rotate around, here's 5 pi over 6, I'm going to start there. Because if I start at the 5 pi over 6 and then go the whole way around, I'm going to get the whole thing. Are you coming with me? I'm not, okay. So this one's going to have to be 5 pi over 6 until I get all the way back around to here. So if we start at 5 pi over 6, if we go around, this is 2 pi. We have to go further than that. So it would be 2 and pi over 6. So how would you write 2? Because you can't write 2 and a 6th pi. That's not something we like. That's not a thing. We don't do that. Like, what would that be as a fraction of pi? Good. 13 pi over 6. I will not make you do the antiderivative for that one because it's kind of nasty. As long as you can get the setup, usually you'll be okay.